In the beginning, there was no matter as we know it. No atoms, no molecules, no solid particles of any kind. Yet the universe was far from empty. It was filled with something far more fundamental and powerful than matter. Pure energy in its most concentrated and violent form. Picture the moment of the Big Bang not as an explosion in space, but as the sudden appearance of space itself, bursting forth from a point smaller than a proton, yet containing all the energy that would ever exist in our universe. In that first instant, 13.8 billion years ago, temperatures soared beyond 100 million trillion degrees. At such temperatures, the very concept of matter becomes meaningless. Energy ruled supreme. This was not the gentle energy we experience in our daily lives, the warmth of sunlight, or the glow of a fire. This was energy so intense that it could spontaneously create particles from nothing but its own abundance. According to Einstein's famous equation E equals mc squared, energy and mass are interchangeable. When energy concentrates enough, it can literally transform into matter. In the primordial universe, this transformation happened trillions of times every second. But what do we mean when we say the universe came from nothing? This is perhaps one of the most misunderstood concepts in all of cosmology. When physicists speak of nothing, they do not mean the absolute void that philosophers might imagine. Even empty space, what we call the quantum vacuum, seethes with activity. Virtual particles pop in and out of existence, borrowing energy from the vacuum itself for the briefest of moments before annihilating back into nothingness. The quantum vacuum is not truly empty, but rather the lowest energy state that space can achieve. It is filled with quantum fields that permeate every point in the universe. These fields are not matter, but they are something, the fundamental substrate from which all particles emerge. Think of them as invisible threads woven through the fabric of space, vibrating with potential energy. In the earliest moments after the Big Bang, these quantum fields were stretched and amplified to incredible proportions. Tiny fluctuations in the fields, normally invisible and ephemeral, were blown up to macroscopic scales. These fluctuations carried energy, and that energy began the process of creating the first particles. The universe was so hot and dense that normal physics barely applied. The four fundamental forces of nature that govern our world today, gravity, electromagnetism, and the strong and weak nuclear forces, were likely unified into a single all-encompassing force. As the universe expanded and cooled, these forces began to separate, each taking on its distinct character. In those first moments, time itself behaved strangely. The Planck time, about 10 to the minus 43 seconds after the Big Bang, represents the earliest moment we can meaningfully discuss with our current understanding of physics. Before this time, our theories break down completely. Space and time themselves may have been emerging from something even more fundamental. As the universe expanded, it cooled rapidly. This cooling was not like opening a refrigerator door, but rather like the expansion of a gas, where the same amount of energy spreads over an ever-increasing volume of space. The temperature dropped from inconceivable heights to merely billions of degrees in the first fraction of a second. This cooling was crucial because it allowed the first phase transitions to occur. Just as water vapor condenses into liquid when cooled, the unified forces of the early universe began to separate as temperatures dropped. First, gravity separated from the other forces, then the strong nuclear force split off, leaving electromagnetism and the weak nuclear force temporarily united. During this period, the universe underwent a phase of exponential expansion called inflation. In less than 10 to the minus 30 seconds, the universe grew by a factor of at least 10 to the power of 26, possibly much more. This inflation stretched the quantum fluctuations we mentioned earlier across vast distances. setting the stage for the large-scale structure we see in the universe today. The energy driving inflation came from a special kind of field called the inflaton field. Like all quantum fields, it could exist in different energy states. When it was in a high energy state, it caused space itself to expand exponentially. When it finally decayed to a lower energy state, it released its stored energy in a process called reheating. This reheating was the true birth of matter and radiation as we know them. The inflaton field's energy transformed into a hot, dense soup of particles and antiparticles. Photons, electrons, neutrinos, quarks, and their corresponding antiparticles filled the universe. For the first time, the cosmos contained recognizable particles, though they were nothing like the stable atoms we see today. The temperature after reheating was still astronomical, perhaps 10 to the power of 15 degrees, hot enough to create and destroy massive particles with ease. At such temperatures, particles moved at nearly the speed of light, colliding and transforming into other particles in a cosmic dance of creation and destruction. Einstein's equation E equals mc squared was operating at full force. Energy continuously converted into particle-antiparticle pairs, while these pairs annihilated back into energy. The universe was in a state of thermal equilibrium, where the rate of particle creation exactly balanced the rate of destruction. This balance was maintained by the incredible energy density of the early universe. There was so much energy available that creating massive particles was effortless. Even particles that today require enormous particle accelerators to create were produced routinely in the primordial fireball. Yet even in this chaotic maelstrom, certain conservation laws held firm. Electric charge, for instance, remained conserved. For every negatively charged particle created, a positively charged particle appeared as well. Energy and momentum were conserved in every collision and transformation. These conservation laws would prove crucial in determining what survived from the early universe. As the universe continued to expand and cool, different types of particles began to freeze out of thermal equilibrium. The heaviest particles disappeared first, as there was no longer enough energy to create them. Lighter particles persisted longer, but even they would eventually cease to be produced as the temperature dropped below their threshold energies. The story of how atoms formed from this energy-rich beginning is really the story of how order emerged from chaos, how the wild democracy of the early universe gave way to the structured hierarchy we see today. It is a story of survival, where only the hardiest particles would persist long enough to become the building blocks of matter. The transition from pure energy to the first stable particles marks one of the most important phase changes in the history of the universe. It was the moment when the abstract became concrete, when mathematical fields and energy densities began their transformation into the tangible matter that would eventually form stars, planets, and life itself. This transformation did not happen all at once, but unfolded over several distinct phases, each with its own unique physics and challenges. The particles that survived this transition would face even greater trials ahead, including a nearly complete annihilation that would destroy almost everything that had been created. Understanding this energy-drenched beginning helps us appreciate the remarkable journey that led from the quantum foam of the early universe to the complex atoms that make up our bodies today. Every proton in our DNA, every electron in our cells, every neutron in our bones has a history that stretches back to these first moments after the Big Bang. The universe began not with nothing, but with everything concentrated into an infinitesimal point. From that point, space expanded, energy cooled, and the first tentative steps toward matter began. It was a beginning pregnant with all the possibilities that would unfold over billions of years. A beginning that contained within it the seeds of stars, galaxies, planets, and ultimately, conscious beings capable of contemplating their own cosmic origins. The energy that filled the early universe was not lost, but transformed again and again through countless interactions and phase transitions. That same energy, in different forms, continues to flow through our universe today. It powers the fusion reactions in stellar cores, drives the expansion of space itself, and animates the chemistry of life. From this perspective, we are not separate from the cosmos, but intimately connected to it. We are temporary arrangements of energy that first condensed from the quantum vacuum 13.8 billion years ago. We are the universe becoming aware of itself, matter organized into patterns complex enough to contemplate matter's own origins. The story of atoms forming from nothing is really the story of how complexity emerged from simplicity, how the rich tapestry of the modern universe unfolded from an initially featureless state. It is a story that continues today as new stars form, new elements are forged, and new possibilities emerge from the ongoing dance of energy and matter. As we stand on the threshold of understanding these cosmic origins, we can appreciate the profound journey that brought us here. From the quantum foam of the earliest moments to the structured matter of today, the universe has been on an epic quest to organize itself into ever more complex and beautiful forms. We are both the products and the chroniclers of that quest, witnesses to the universe's long journey from energy to atoms to awareness. The first second after the Big Bang was not a single moment, but an entire epoch of cosmic evolution. Within that second, the universe transformed from a realm of pure energy into something beginning to resemble the particle physics we observe today. But this transformation happened so rapidly that each fraction of a second brought dramatic changes to the fundamental nature of reality itself. At 1/10,000,000th of a second after the Big Bang, the universe had cooled to about 1 trillion degrees. This might seem impossibly hot, but it represented a dramatic cooling from the initial temperatures. At this temperature, something remarkable happened. The universe became cool enough for quarks to exist as distinct particles, no longer melting back into pure energy the instant they formed. Quarks are among the most fundamental building blocks of matter, the constituents from which protons and neutrons are made. But in the early universe, quarks did not immediately combine into these familiar particles. Instead, they existed in a state unlike anything we see in nature today, a phase of matter called quark-gluon plasma. Imagine a soup so hot and dense that the ingredients cannot separate into distinct flavors. The quark-gluon plasma was exactly such a soup, a seething ocean of quarks and the particles that bind them together, called gluons. In this plasma, quarks moved freely through space, unbound by the forces that normally confine them within protons and neutrons. To understand why this phase was so unusual, we need to appreciate one of the strangest features of the strong nuclear force. Unlike other forces in nature, which weaken with distance, the strong force actually grows stronger as quarks are pulled apart. It is like trying to separate two balls connected by a rubber band that becomes stiffer the more you stretch it. This peculiar property means that in our cold universe today, quarks can never exist in isolation. Try to pull a single quark out of a proton, and the energy required becomes so large that it creates new quark-antiquark pairs instead. The isolated quark you were trying to extract ends up bound to one of these new quarks, forming a new particle, while the antiquark binds with the remaining quarks in the original proton. But in the quark-gluon plasma of the early universe, conditions were so extreme that this normal behavior broke down. The temperature was so high, and the density so great, that quarks were constantly surrounded by other quarks and gluons. The strong force, confused by this crowd, could not effectively confine any individual quark. This plasma was not a static soup, but a dynamic, churning maelstrom. Quarks and gluons collided trillions of times per second, transforming into other particles and back again. Gluons could split into quark-antiquark pairs, while quarks and antiquarks could annihilate into gluons. The distinction between matter and the forces that govern matter became blurred. At this time, there were 6 different types of quarks, each with its own antiparticle counterpart. The lightest quarks, called up and down quarks, would eventually become the building blocks of protons and neutrons. The heavier quarks, strange, charm, bottom and top, were also present, but would not survive long as the universe cooled. The gluons that mediated the strong force were themselves participants in the interactions they were supposed to govern. Unlike photons, which carry the electromagnetic force but do not interact with each other, gluons carry strong force charge and can interact with themselves. This self-interaction made the quark-gluon plasma even more complex and dynamic. As the universe continued to expand and cool, the quark-gluon plasma began to change. The temperature dropped, the density decreased, and the conditions that allowed quarks to move freely started to disappear. The universe was approaching a critical transition, one of the most important phase changes in cosmic history. At about 1 microsecond after the Big Bang, when the temperature had fallen to about 100 billion degrees, the quark-gluon plasma underwent what physicists call the QCD phase transition. QCD stands for quantum chromodynamics, the theory that describes the strong nuclear force. This transition was like the moment when water vapor condenses into droplets, except that instead of molecules clumping together, quarks were suddenly confined within individual particles. The transition was remarkably swift. In a tiny fraction of a second, the free-floating quarks found themselves locked inside the particles we know as protons and neutrons. The anarchic democracy of the quark-gluon plasma gave way to the structured hierarchy of confined particles. But not all quarks made it through this transition. The heavier quarks, which required more energy to create, began to disappear as the universe cooled. Strange quarks, charm quarks, bottom quarks, and top quarks all decayed into lighter particles or were no longer created in collisions. Only the lightest quarks, up and down, survived in significant numbers. The process by which quarks became confined into protons and neutrons is called hadronization. Hadrons are particles made of quarks bound together by the strong force. The most common hadrons are baryons, which contain 3 quarks, and mesons, which contain a quark and an antiquark. The proton, made of 2 up quarks and 1 down quark, became the most stable baryon. Its positive electric charge came from the fact that up quarks carry a charge of positive 2/3, while down quarks carry negative 1/3. 2 up quarks contribute positive 4/3. 1 down quark contributes negative 1/3, for a total charge of positive 1. The neutron, made of 2 down quarks and 1 up quark, became the second most important baryon. Its total electric charge was 0, making it electrically neutral. 2 down quarks contribute negative 2/3. 1 up quark contributes positive 2/3, summing to 0. But the story of hadronization was not simply one of quarks finding stable homes. Many other types of hadrons were created during this process, most of them highly unstable. Particles called pions, kaons, and countless others briefly populated the universe before decaying into more stable forms. The newly formed hadrons did not exist in isolation, but were part of a hot, dense gas. This hadronic gas was still incredibly energetic, with particles moving at significant fractions of the speed of light. Collisions were frequent and violent, with particles constantly being created and destroyed. Among the most important reactions in this hadronic gas were those involving protons and neutrons themselves. Free neutrons are unstable, decaying into protons, electrons, and neutrinos with a half-life of about 15 minutes. But in the dense, hot conditions of the early universe, this decay was balanced by reactions that converted protons back into neutrons. The balance between protons and neutrons was crucial for the future of the universe. If there had been only protons, no complex nuclei could have formed. If there had been only neutrons, they would have decayed away completely. The precise ratio of protons to neutrons was determined by the temperature and density conditions during this epoch. As the universe continued to cool, the reactions that converted protons to neutrons became less frequent. Protons, being slightly lighter than neutrons, became increasingly favored. By the time the universe was about 1 second old, the ratio had stabilized at about 7 protons for every neutron. This might seem like a minor detail, but it would prove to be one of the most important factors in determining the composition of the universe. The ratio of protons to neutrons would directly determine how much hydrogen and helium could be formed in the next phase of cosmic evolution. The transition from quark-gluon plasma to hadronic matter represents one of the most dramatic phase changes in the history of the universe. In the span of microseconds, the fundamental character of matter changed from a soup of elementary particles to a gas of composite objects that would be recognizable to modern physicists. Yet even as this transition created the first stable protons and neutrons, the universe was still far from containing atoms. The temperature was still billions of degrees, far too hot for electrons to bind to nuclei. The newly formed hadrons existed in a sea of other particles, including electrons, positrons, neutrinos, and photons. This mixture was still in thermal equilibrium, meaning that all the different types of particles had the same average energy. Collisions were so frequent that no particle could maintain an energy very different from the average for long. The universe was like a perfectly stirred soup, with energy constantly being redistributed among all the ingredients. But thermal equilibrium also meant that the universe was rapidly approaching another critical juncture. The expansion and cooling would soon reach a point where certain particles would begin to fall out of equilibrium, setting the stage for one of the most dramatic episodes in cosmic history. The particles that had survived the transition from energy to matter were about to face an even greater challenge. In the coming moments, matter and antimatter would engage in a cosmic battle of annihilation that would determine whether anything at all would survive to form the atoms of the future. The quark-gluon plasma had been a state of pure possibility, where all types of particles could exist in equal abundance. The hadronic gas that followed began to impose the first constraints, favoring some particles over others based on their masses and interaction strengths. But the great winnowing was yet to come. As we look back on this epoch from our vantage point 13.8 billion years later, we can appreciate how precarious the existence of matter truly was. The quarks that would eventually become part of our bodies were once free-swimming constituents of a plasma hotter than the core of any star. They underwent confinement in a phase transition more dramatic than any we observe in nature today. The protons and neutrons that emerged from this transition carried within them the potential for all future complexity. They were the first composite objects in the universe, the first examples of parts combining to create wholes with properties different from their constituents. In this sense, they were the ancestors of molecules, cells, organisms, and ultimately conscious beings, capable of reconstructing their own cosmic history. The journey from quarks to hadrons was a journey from simplicity to complexity, from fundamental to composite, from anarchic to organized. It was the first step in the long process by which the universe learned to build structures, to create stable arrangements of matter that could persist and evolve over cosmic time. But this journey was far from over. The newly formed protons and neutrons were about to enter the most dangerous period of their existence, a time when almost all of them would be destroyed in the ultimate battle between matter and antimatter. Only a tiny fraction would survive to become the building blocks of the atoms that fill our universe today. As the universe entered its second of existence, It faced the most catastrophic crisis in its entire history. The cosmos was about to witness an event so destructive that it would erase almost everything that had been created during the preceding moments of cosmic evolution. This was the Great Annihilation, a period when matter and antimatter engaged in a battle to the death that nearly left the universe empty and lifeless. To understand the magnitude of this crisis, we must first appreciate what antimatter is and why its existence posed such a fundamental threat to everything we see in the universe today. For every type of particle that exists, nature provides an antiparticle with exactly opposite properties. The electron has an anti-electron, called a positron, with the same mass but opposite electric charge. The proton has an antiproton with the same mass but negative charge instead of positive. When a particle meets its corresponding antiparticle, they annihilate each other completely, converting their entire mass into pure energy according to Einstein's equation E equals mc squared. This is not a chemical reaction where molecules rearrange, nor a nuclear reaction where atomic nuclei split or fuse. This is total conversion of matter into energy, the most complete form of destruction possible in the universe. In the early universe, particles and antiparticles were created in exactly equal numbers. Every time a collision produced a proton, it also produced an antiproton. Every electron came with a positron. Every neutron had its anti-neutron counterpart. This perfect symmetry between matter and antimatter seemed to be a fundamental law of physics, written into the very structure of reality. But this symmetry spelled doom for the universe. If matter and antimatter were truly equal, they should have annihilated each other completely, leaving behind nothing but a sea of photons and perhaps some neutrinos. The universe should have become a brilliant flash of light that gradually faded as it expanded and cooled, containing no atoms, no stars, no planets, and certainly no life. As the universe cooled below the threshold for creating new proton-antiproton pairs, around 1 second after the Big Bang, the annihilation began in earnest. The temperature had dropped to about 10 billion degrees, still incredibly hot, but no longer sufficient to spontaneously create the heavy particles from photon collisions. The existing protons and antiprotons were now living on borrowed time. The annihilation process was swift and merciless. When a proton encountered an antiproton, they would spiral into each other and vanish in a burst of gamma rays. The same fate awaited neutrons and antineutrons, electrons and positrons, and every other particle-antiparticle pair. The universe became a cosmic battleground where matter and antimatter fought to mutual destruction. Picture the scene. Trillions upon trillions of particles racing through space at nearly the speed of light, seeking their opposite counterparts for mutual annihilation. Each encounter resulted in a flash of pure energy, as mass converted completely into radiation. The universe blazed with the light of countless annihilations, each one erasing a tiny piece of the matter that had so laboriously been assembled from the primordial energy. The efficiency of this destruction was almost perfect. For every billion particles of matter, there were billion particles of antimatter. They found each other with devastating regularity, their opposite charges drawing them together like cosmic magnets programmed for mutual suicide. Billion by billion, they cancelled each other out, converting their substance into electromagnetic radiation. But somehow, impossibly, the universe survived this cosmic holocaust. When the annihilation was over, when the last antiproton had found its corresponding proton and the final positron had met its electron, something remained. For reasons that physicists are still working to understand completely, there was a tiny excess of matter over antimatter. Out of every billion particles, just one extra particle of matter survived the annihilation. This minuscule imbalance, this cosmic rounding error of 1 part in a billion, made all the difference. It is the reason atoms exist today. It is the reason stars shine and planets form. It is the reason you exist to contemplate this story. every proton in your body is a survivor of this great annihilation, a refugee from the most complete genocide in cosmic history. The mystery of why this imbalance existed is known as the baryon asymmetry problem, and it remains one of the deepest puzzles in cosmology. Baryons are particles like protons and neutrons, made of three quarks bound together. The standard model of particle physics provides no explanation for why there should be more baryons than antibaryons in the universe. Several conditions must be met for such an asymmetry to develop. First, there must be processes that can violate baryon number conservation, allowing the total number of baryons to change. Second, there must be a violation of charge conjugation and parity symmetry, meaning that particles and antiparticles must behave slightly differently under certain conditions. Third, these processes must occur when the universe is not in thermal equilibrium, so that the asymmetry cannot be erased by statistical fluctuations. The Russian physicist Andrei Sakharov first outlined these conditions in 1967, but finding specific mechanisms that satisfy all three requirements has proven challenging. The standard model of particle physics contains some processes that violate these symmetries, but they are far too weak to account for the observed matter-antimatter asymmetry. One promising explanation involves the physics of neutrinos, those ghostly particles that barely interact with anything else in the universe. Heavy neutrinos in the early universe might have decayed asymmetrically, producing slightly more matter than antimatter. Another possibility involves exotic particles or forces that existed only in the extreme conditions of the very early universe. Some theories propose that the asymmetry was generated during the inflationary epoch, when quantum fluctuations were stretched across cosmic scales. Others suggest it arose during phase transitions, when fundamental forces separated from their unified state. The truth might involve physics beyond our current understanding, requiring new theories of quantum gravity or extra dimensions. Regardless of the specific mechanism, the consequences of this tiny asymmetry were enormous. The surviving matter, roughly 1/1000th of what originally existed, became the raw material for everything we see in the universe today. Every star, every planet, every atom in your body traces its lineage back to these few survivors of the Great Annihilation. The photons produced by the annihilation did not simply disappear. They became part of the cosmic microwave background radiation that we can still observe today. When you tune a radio to a frequency that picks up static, about 1% of that static comes from the afterglow of matter-antimatter annihilation that occurred 13.8 billion years ago. You are literally listening to the echo of cosmic genocide. The energy released during the annihilation was staggering. Each particle-antiparticle pair that annihilated released energy equal to twice the rest mass of the particles involved. With trillions upon trillions of such annihilations occurring throughout the observable universe, the total energy release dwarfed anything we can imagine. It was as if the universe had detonated a bomb made of pure matter, converting almost all of its substance into radiant energy. This energy had profound effects on the evolution of the universe. It helped drive the expansion of space itself, contributing to the cosmic recession that continues today. It also heated the remaining matter to incredible temperatures, ensuring that even after the annihilation was complete, conditions remained far too hot for atoms to form. The surviving particles found themselves in a universe transformed by the annihilation. The density of matter had dropped by a factor of 1 billion, from the incredibly dense soup of the first second to a much more rarefied gas of protons, neutrons, electrons, and photons. The universe had become matter-poor and radiation-rich, with photons outnumbering matter particles by billions to 1. This radiation-dominated era would persist for thousands of years, with the energy density of photons exceeding that of matter particles. The universe was essentially a hot, glowing gas, in which matter played only a minor role. Gravity, which would later become the architect of cosmic structure, was still too weak to overcome the thermal motion of particles and the pressure of radiation. The Great Annihilation also established the basic inventory of particles that would participate in all subsequent cosmic evolution. The survivors included protons, neutrons, electrons, photons, and neutrinos. More exotic particles had either annihilated completely or decayed into these stable forms. The universe had been simplified, reduced to its most essential components. Among the survivors, protons proved to be remarkably stable. As far as we know, protons do not decay, or if they do, their lifetime exceeds 10 to the 34 years, far longer than the current age of the universe. This stability was crucial for the formation of atoms and everything that followed. Without stable protons, no atomic nuclei could persist long enough to capture electrons and form neutral atoms. Neutrons, by contrast, were less stable. Free neutrons decay into protons, electrons, and neutrinos with a half-life of about 15 minutes. But in the dense, hot conditions following the annihilation, many neutrons were still converting back and forth with protons through weak nuclear interactions. The exact ratio of neutrons to protons would prove critical for the next phase of cosmic evolution. Electrons, being much lighter than protons and neutrons, were moving at relativistic speeds in the hot post-annihilation universe. They could not yet bind to atomic nuclei because their thermal energy was far too high to be trapped by electromagnetic forces. They existed as a free electron gas, contributing to the electrical conductivity of the cosmic plasma. The photons produced by annihilation, along with those that had existed since the earliest moments, formed a thermal radiation field that permeated all of space. These photons were constantly interacting with the free electrons, scattering off them and exchanging energy. This interaction kept the radiation and matter in thermal equilibrium, ensuring that both had the same temperature. Neutrinos, those elusive particles that barely interact with anything, began to decouple from the rest of the matter and radiation around this time. Because they interact only through the weak nuclear force, neutrinos could travel increasingly long distances without scattering. They began to stream freely through the universe, carrying with them a record of conditions during the annihilation epoch. The cosmic neutrino background that was established during this period still exists today, though it has cooled to just a few degrees above absolute zero. Detecting these relic neutrinos remains one of the holy grails of experimental cosmology, as they would provide a direct window into the conditions that existed when the universe was just 1 second old. As the universe continued to expand and cool, the aftermath of the Great Annihilation set the stage for the next crucial phase of cosmic evolution. The surviving matter particles were about to begin a process that would create the first atomic nuclei, the next step on the long road toward atoms and the complex chemistry that makes life possible. But the shadow of the annihilation would hang over all future cosmic evolution. The universe had been forever changed by this near-total destruction. What remained was precious precisely because so much had been lost. The rarity of matter compared to radiation, the vast emptiness of space, the delicate balance of particles that allows stars to shine and planets to form, all can be traced back to those first few seconds when matter and antimatter fought their cosmic war. The survivors of the Great Annihilation were not just the building blocks of future atoms. They were the inheritors of a universe that had been through the ultimate test of existence. They had witnessed the near destruction of everything and had somehow persevered. In a very real sense, every atom in your body is a monument to survival, a testament to the improbable victory of something over nothing that occurred in the first moments of cosmic time. 3 minutes after the Big Bang, the universe reached a critical temperature threshold that would determine the chemical composition of the cosmos for billions of years to come. At this moment, roughly 180 seconds into cosmic time, the temperature had cooled to about 1 billion degrees. This was still unimaginably hot by earthly standards, hotter than the core of any star that would ever exist, but it was cool enough for one of the most important processes in cosmic history to begin: the formation of the first atomic nuclei. Up until this point, the universe had been too hot for protons and neutrons to stick together. Any time they approached each other closely enough for the strong nuclear force to bind them, the intense thermal energy would immediately tear them apart again. It was like trying to build with blocks while someone constantly shook the table. But as the 3-minute mark approached, the cosmic table finally became steady enough for nuclear construction to begin. The process that was about to unfold is called Big Bang nucleosynthesis, and it represents one of the greatest triumphs of modern cosmology. Not only can we calculate exactly what should have happened during those crucial first 20 minutes of nuclear fusion, but we can observe the products of those reactions throughout the universe today. The agreement between theory and observation is so precise that it provides one of the strongest confirmations of the Big Bang model itself. The story of Big Bang nucleosynthesis begins with the inventory of particles that survived the Great Annihilation. The universe contained protons, neutrons, electrons, photons, and neutrinos in well-defined proportions. The ratio of neutrons to protons had stabilized at about 1 neutron for every 7 protons by the time nucleosynthesis began. This ratio had been determined by the weak nuclear interactions that converted neutrons to protons and vice versa during the earlier, hotter phases of cosmic evolution. The first nuclear reaction to occur was the formation of deuterium, also known as heavy hydrogen. Deuterium consists of 1 proton and 1 neutron bound together by the strong nuclear force. This might seem like a simple step, but it was actually a bottleneck that delayed nucleosynthesis for several minutes after conditions first became cool enough for nuclear reactions to proceed. The problem was that deuterium nuclei are relatively fragile. They can be broken apart by photons with energies corresponding to temperatures of several billion degrees. Even though the average temperature had dropped below this threshold, there were still many high-energy photons in the thermal radiation field that could destroy deuterium nuclei as quickly as they formed. This is known as the deuterium bottleneck, and it prevented significant nuclear synthesis until the temperature dropped low enough that very few photons could break apart deuterium. Once deuterium could survive long enough to participate in further reactions, nuclear fusion proceeded rapidly. Deuterium nuclei collided with protons to form helium-3, which contains 2 protons and 1 neutron. They also collided with other deuterium nuclei to form either tritium, containing 1 proton and 2 neutrons, or helium-3, through a different reaction pathway. Tritium is radioactive, with a half-life of about 12 years, but in the conditions of the early universe, it quickly fused with deuterium to form helium-4, the most common isotope of helium. Helium-4, with 2 protons and 2 neutrons, is an exceptionally stable nucleus. Its binding energy per nucleon is higher than that of any lighter nucleus, making it the preferred end product of Big Bang nucleosynthesis. The nuclear reaction network that produced these light elements was remarkably efficient. Almost all of the neutrons that existed at the beginning of nucleosynthesis ended up incorporated into helium-4 nuclei. Since neutrons made up about 1/8 of the nuclear particles, and each helium-4 nucleus contains 2 neutrons, approximately 1/4 of all nuclear matter by mass was converted into helium-4. This 25% helium abundance is one of the most important predictions of Big Bang cosmology. When astronomers measure the helium content of the most primitive stars and gas clouds in the universe, they find almost exactly this proportion. Stars can produce additional helium through fusion in their cores, but they start with the primordial 25% that was forged in the first 20 minutes of cosmic time. The production of helium-4 was so favored that it consumed virtually all available neutrons. However, some deuterium survived, because not every deuterium nucleus found a reaction partner before nucleosynthesis ended. The amount of surviving deuterium depended critically on the density of matter in the universe. In a denser universe, deuterium nuclei would be more likely to encounter other nuclei and be consumed in further reactions. In a less dense universe, more deuterium would survive. This relationship between matter density and deuterium abundance provides another precise test of cosmological models. By measuring the amount of deuterium in primordial gas clouds, astronomers can determine the density of ordinary matter in the universe with remarkable accuracy. The results agree beautifully with independent measurements from the cosmic microwave background radiation and other sources. Small amounts of lithium-7 were also produced during Big Bang nucleosynthesis. Lithium-7 contains 3 protons and 4 neutrons, and it was formed primarily through the fusion of helium-4 with tritium, or through the fusion of helium-3 with helium-4. The predicted abundance of lithium-7 is about 1/10,000,000th that of hydrogen, making it extremely rare but still detectable in the most ancient stars. Interestingly, there is a small discrepancy between the predicted and observed amounts of lithium-7, with observations showing somewhat less lithium than theory predicts. This lithium problem is one of the few remaining puzzles in Big Bang nucleosynthesis, and it may indicate that our understanding of the nuclear reactions involved is incomplete, or that some subsequent process has destroyed primordial lithium. One of the most remarkable features of Big Bang nucleosynthesis is what did not happen. Despite the high temperatures and densities involved, no elements heavier than lithium were produced in significant quantities. This might seem surprising, given that the conditions were more extreme than those in the cores of even the most massive stars. The reason lies in the peculiar properties of nuclear physics and the rapid expansion of the universe. To build elements heavier than lithium, nuclear reactions must bridge certain gaps in the chain of stable nuclei. There are no stable nuclei with mass 5 or mass 8, which creates bottlenecks in the fusion process. In stellar cores, these gaps can be bridged by rare 3-body reactions, such as the triple alpha process that fuses 3 helium-4 nuclei to make carbon-12. But these reactions require high densities and long time scales that were not available in the rapidly expanding early universe. The temperature and density dropped too quickly for the complex reaction networks needed to produce heavy elements. By the time helium-4 had been synthesized, about 20 minutes after the Big Bang, the universe had cooled and expanded to the point where nuclear reactions essentially ceased. The cosmic nuclear furnace had burned out, leaving behind a universe composed of roughly 75% hydrogen and 25% helium by mass, with trace amounts of deuterium and lithium. This elemental composition would remain essentially unchanged for hundreds of millions of years until the first stars formed and began producing heavier elements through stellar nucleosynthesis. The universe entered what cosmologists call the Dark Ages, a period when no sources of light existed except the gradually cooling radiation left over from the Big Bang itself. The precision with which Big Bang nucleosynthesis can be calculated is truly remarkable. Using only the known laws of nuclear physics and the observed expansion rate of the universe, cosmologists can predict the abundances of light elements to within a few percent. The fact that these predictions agree so well with observations provides powerful evidence that our understanding of the early universe is fundamentally correct. The success of Big Bang nucleosynthesis calculations also constrains many aspects of cosmological models. The observed abundances of light elements require that the universe have a specific density of ordinary matter, expand at a particular rate, and contain a definite number of types of neutrinos. These constraints have been crucial in establishing the standard model of cosmology and ruling out alternative theories. One particularly important constraint comes from the observed helium abundance. If the universe had expanded faster during nucleosynthesis, there would have been less time for neutrons to decay into protons, leaving more neutrons available to form helium. If it had expanded slower, more neutrons would have decayed, reducing the helium yield. The observed 25% helium abundance requires a very specific expansion rate that matches other independent measurements. The number of neutrino species also affects nucleosynthesis outcomes. More types of neutrinos would increase the energy density of the universe during nucleosynthesis, speeding up the expansion and affecting the neutron-to-proton ratio. The observed light element abundances indicate that there are exactly 3 types of light neutrinos, a result that was later confirmed by particle physics experiments. Big Bang nucleosynthesis also provides insights into the nature of dark matter, the mysterious substance that makes up most of the matter in the universe. If dark matter consisted of ordinary particles like protons and neutrons, it would have participated in nucleosynthesis and affected the production of light elements. The observed abundances indicate that dark matter must be made of something else entirely, particles that interact only gravitationally and do not take part in nuclear reactions. The nuclear ashes of Big Bang nucleosynthesis became the raw material for the first generation of stars. When gravity finally overcame thermal pressure and began forming the first stellar condensations, these stars were composed almost entirely of hydrogen and helium. They contain no carbon, no oxygen, no silicon, no iron, none of the heavy elements that make rocky planets and biological chemistry possible. These first stars, known as population 3 stars, were likely much more massive than typical stars today. The lack of heavy elements meant that the gas clouds from which they formed could not cool as efficiently, preventing fragmentation into smaller pieces. As a result, the first stars may have been tens or even hundreds of times more massive than our Sun, burning through their nuclear fuel in just a few million years before exploding as supernovae. When these first stars died, they enriched the surrounding gas with heavy elements produced in their cores and during their explosive deaths. Subsequent generations of stars formed from gas that was gradually enriched with heavier elements, eventually leading to the rich chemical diversity we see in the universe today. But the foundation for all of this complexity was laid in the first 20 minutes of cosmic time, when the universe briefly became a nuclear reactor operating on a cosmic scale. The light elements produced during Big Bang nucleosynthesis provided the fuel for the first stars and set the initial conditions for billions of years of cosmic chemical evolution. The story of Big Bang nucleosynthesis reminds us how finely tuned the conditions must have been for our universe to evolve as it did. If the strong nuclear force had been slightly different, deuterium might have been too unstable to form, preventing all subsequent nuclear fusion. If the weak force had been stronger or weaker, the neutron-to-proton ratio would have been different, dramatically altering the helium abundance and the properties of the first stars. The success of stellar evolution depends critically on the approximately 3-to-1 ratio of hydrogen to helium established during Big Bang nucleosynthesis. Stars like our Sun burn hydrogen into helium for most of their lives, but they also require the presence of some heavy elements to regulate their internal structure and enable the formation of planetary systems. The cosmic recipe written during the first 20 minutes made all subsequent stellar and planetary evolution possible. As we look back on this remarkable epoch from our perspective 13.8 billion years later, we can appreciate how much of the universe's future was determined in those crucial first minutes when atomic nuclei began to form. The protons and neutrons that survived the Great Annihilation had finally found stable configurations that could persist as the universe continued to cool and expand. They had taken the first essential step on the long journey toward atoms, molecules, and the chemistry of life. After the brief cosmic forge of Big Bang nucleosynthesis had cooled and the last nuclear reactions had flickered out, the universe entered a long epoch that would last for hundreds of thousands of years. This was an age unlike any that would follow, a time when the cosmos was filled with brilliant light, but remained fundamentally transparent to that light only in the smallest scales. It was the era of the cosmic plasma, when electrons roamed free and atoms as we know them could not yet exist. The universe at this time was still incredibly hot by any earthly standard, with temperatures ranging from several 100,000 degrees down to a few thousand degrees, as cosmic expansion continued its relentless cooling effect. These temperatures were far too high for electrons to settle into stable orbits around atomic nuclei. Instead, electrons zipped through space as independent particles, creating what physicists call a plasma state of matter. To understand why this prevented atom formation, we must consider the delicate balance required for an electron to orbit a nucleus. The electromagnetic attraction between the negatively charged electron and positively charged nucleus must overcome the electron's kinetic energy of motion. In the hot plasma of the early universe, electrons were moving far too rapidly for any nucleus to capture and hold them. It was like trying to catch a speeding bullet with a butterfly net. This plasma was not dark, but blazed with intense radiation. The universe was filled with photons of all energies, from low-energy radio waves to high-energy gamma rays, forming what physicists call a thermal spectrum. These photons had been created during the matter-antimatter annihilation and continue to be produced by various high-energy processes in the plasma. The energy density of this radiation actually exceeded that of matter particles, making this a radiation-dominated era in cosmic history. The free electrons in the plasma played a crucial role in shaping the properties of this cosmic light. Whenever a photon encountered an electron, it would scatter off it through a process called Thomson scattering. This scattering was extremely efficient because electrons are charged particles that interact strongly with electromagnetic radiation. A typical photon could travel only a short distance before bouncing off an electron and changing direction. Imagine trying to see through a thick fog where every droplet of water redirects light in a new direction. The cosmic plasma was like such a fog, but instead of water droplets, it contained free electrons that scattered light continuously. This made the universe opaque to its own radiation. Even though space was filled with brilliant light, that light could not travel far in straight lines because it was constantly being redirected by electron collisions. The constant scattering of photons by electrons had profound consequences for the structure and evolution of the early universe. It meant that radiation and matter were tightly coupled together, maintaining the same temperature and moving together as a single fluid. The photons could not escape from regions of higher density, so radiation pressure prevented matter from collapsing under its own gravity to form the first stars and galaxies. This tight coupling between radiation and matter created acoustic waves that propagated through the cosmic plasma. Regions of slightly higher density would begin to collapse under gravity, but the increased radiation pressure would push back, creating oscillations similar to sound waves in air. These cosmic sound waves left their imprint on the distribution of matter and would eventually become visible as patterns in the cosmic microwave background radiation. The plasma itself was electrically neutral on large scales, containing equal numbers of positive and negative charges. The positively charged nuclei, primarily hydrogen and helium, moved more slowly than the lightweight electrons due to their much greater mass. This created a complex dance of charged particles, with electrons darting rapidly between the more ponderous nuclei, while photons bounced continuously off the electron population. The temperature of this plasma decreased steadily as the universe expanded, but the cooling was gradual and uniform. Unlike the rapid changes that had characterized the first few minutes after the Big Bang, This era was marked by smooth, predictable evolution. The laws of thermodynamics governed the cosmic cooling, with temperature dropping in inverse proportion to the scale factor of the universe. During this period, the universe was remarkably homogeneous and isotropic, meaning it looked essentially the same in all directions and at all locations. The constant scattering of photons by electrons acted like a cosmic mixer, ensuring that energy was rapidly redistributed and preventing large-scale structure from forming. Any initial irregularities in density or temperature were quickly smoothed out by the efficient transport of energy through radiation. Yet beneath this apparent uniformity, tiny quantum fluctuations from the inflationary epoch were slowly growing. These fluctuations, stretched to enormous scales during cosmic inflation, provided the seeds for all future structure in the universe. They appeared as minute variations in density, typically less than 1 part in 100,000, that would eventually grow into galaxies, stars, and planets. The gravitational effects of these density fluctuations were competing with the smoothing effects of radiation pressure. In regions where matter was slightly denser than average, gravity tried to pull more matter in, while radiation pressure tried to push it out. The outcome of this competition depended on the size of the fluctuation and the properties of the cosmic fluid. For fluctuations smaller than a critical scale called the Jeans length, radiation pressure dominated and prevented gravitational collapse. But fluctuations larger than this scale could grow slowly even during the radiation-dominated era. The Jeans length itself was enormous during this period, comparable to the size of galaxy clusters today, so only the larger scale fluctuations could grow. The cosmic plasma was also a perfect conductor of electricity. The abundance of free charge particles meant that electric fields could not penetrate far into the plasma before being neutralized by charge redistribution. This prevented the formation of large-scale electric or magnetic fields and ensured that electromagnetic forces played only a local role in plasma dynamics. The density of the plasma was steadily decreasing as the universe expanded, but it remained much denser than the interstellar medium we observe today. The number density of particles was trillions of times higher than in the best vacuums we can create on Earth. Yet this was already a dramatic rarefaction compared to the extreme densities of the first seconds after the Big Bang. As the universe continued to expand and cool, subtle changes began to occur in the properties of the plasma. The most energetic photons gradually shifted to lower energies due to cosmological redshift, and the average kinetic energy of electrons slowly decreased. These changes were imperceptible on short timescales, but accumulated over thousands of centuries to produce measurable effects. The nuclei in the plasma, primarily hydrogen and helium, remained largely unchanged during this period. Nuclear reactions had essentially ceased after Big Bang nucleosynthesis, and the conditions were not extreme enough to alter nuclear structure through other processes. The nuclei simply drifted through the plasma, occasionally interacting with electrons or photons, but maintaining their integrity. Neutrinos, those ghostly particles that barely interact with anything, had already decoupled from the plasma much earlier in cosmic history. They continued to stream freely through the universe, carrying information about conditions during the first second after the Big Bang. By this time, neutrinos were essentially invisible to the rest of the cosmic material, contributing to the energy density, but not participating in the electromagnetic interactions that dominated plasma behavior. The epoch of cosmic plasma was crucial for establishing the initial conditions for structure formation in the universe. The acoustic oscillations in the coupled radiation matter fluid created a characteristic pattern of density fluctuations that would influence where galaxies formed billions of years later. Regions that were compressed during these oscillations had higher densities and would eventually become the sites of the first stars. The plasma era also established the thermal history that would determine when the first atoms could form. The cooling rate was set by the expansion rate of the universe, which in turn depended on the total energy density and the fundamental constants of physics. Any significant deviation from the observed cooling rate would have dramatically altered the subsequent evolution of cosmic structure. Throughout this long period, the universe remained in a state of dynamic equilibrium between expansion and thermal relaxation. The plasma responded to the decreasing density and temperature by maintaining thermal and electrical neutrality while allowing gravitational instabilities to grow slowly on the largest scales. It was a delicate balance that would soon be disrupted by one of the most important transitions in cosmic history. The universe of light and plasma was preparing for a dramatic transformation. As temperatures continued to drop toward a critical threshold of about 3,000 degrees, the cosmic plasma would undergo a phase transition that would fundamentally alter the nature of matter and radiation. The free electrons that had scattered photons for hundreds of thousands of years were about to be captured by atomic nuclei, clearing the cosmic fog and allowing light to travel freely through space for the first time. This transition, called recombination, would mark the end of the plasma era and the beginning of the age of atoms. The universe would suddenly become transparent to its own radiation, and the cosmic microwave background that we observe today would begin its journey across space and time. The long period of plasma dominance was about to give way to a new era in which matter and radiation would finally decouple, setting the stage for the formation of the first cosmic structures. The plasma epoch represents a unique period in cosmic history when the universe was simultaneously filled with light, yet opaque to that light. It was a time of potential energy when the raw materials for complexity existed, but were held in suspension by the extreme conditions. The cooling universe was slowly but inexorably approaching the moment when this potential would be released, allowing atoms to form and the grand story of cosmic structure formation to begin in earnest. At approximately 380,000 years after the Big Bang, the universe reached a pivotal moment that would fundamentally transform the nature of reality itself. The cosmic temperature had cooled to about 3,000 degrees, roughly half the temperature of the Sun's surface. This marked a critical threshold where one of the most important phase transitions in cosmic history was about to begin: the formation of the first atoms. The process is called recombination, though this name is somewhat misleading since electrons and nuclei were combining for the first time rather than recombining. For hundreds of thousands of years, the universe had been too hot for stable atoms to exist. Electrons had sufficient thermal energy to remain free, zipping through space independently of the atomic nuclei that would eventually capture them. But as the cosmic temperature dropped below the ionization energy of hydrogen, the fundamental character of matter was about to change forever. Hydrogen, being the simplest and most abundant element, led this cosmic transformation. A hydrogen atom consists of a single proton nucleus with one electron bound to it by electromagnetic forces. The binding energy that holds this system together is about 13.6 electron volts, which corresponds to a temperature of roughly 160,000 degrees. However, recombination did not begin as soon as the average temperature dropped below this threshold. The reason for this delay lies in the nature of thermal distributions and the abundance of photons in the early universe. Even when the average temperature was below the hydrogen ionization threshold, there were still many high-energy photons capable of immediately ionizing any hydrogen atoms that formed. The universe contained about 1 billion photons for every proton, so even a tiny fraction of high-energy photons in the thermal distribution could prevent atom formation. Recombination finally began in earnest when the temperature dropped low enough that very few photons had sufficient energy to ionize hydrogen. This occurred around 3,000 degrees, significantly lower than the ionization temperature because of the statistical properties of thermal radiation. At this point, electrons began to settle into stable orbits around protons, forming the first neutral hydrogen atoms in cosmic history. The process was not instantaneous, but unfolded over tens of thousands of years. It began with the most tightly bound states, where electrons were captured into the lowest energy orbitals around hydrogen nuclei. These atoms were initially formed in excited states and quickly cascaded down to the ground state, emitting photons in the process. The universe literally glowed with the light of atomic formation as trillions upon trillions of electrons found their nuclear homes. Helium atoms formed somewhat earlier than hydrogen, because helium nuclei carry twice the electric charge of hydrogen nuclei, creating stronger electromagnetic fields that could capture electrons even at slightly higher temperatures. Helium atoms are also more tightly bound than hydrogen, making them more resistant to ionization by thermal photons. However, since hydrogen was about 12 times more abundant than helium, the overall recombination process was dominated by hydrogen atom formation. As electrons combined with nuclei to form neutral atoms, one of the most dramatic changes in cosmic history occurred. The universe suddenly became transparent to light. Throughout the plasma era, photons had been constantly scattered by free electrons, making space opaque despite being filled with radiation. But neutral atoms interact much more weakly with photons than free electrons do, allowing light to travel freely through space for the first time. This transformation was remarkably rapid on cosmic scales. Over a period of just a few tens of thousands of years, the universe went from being completely opaque to essentially transparent. It was as if a cosmic fog that had persisted for hundreds of thousands of years suddenly lifted, revealing a clear view of the universe's structure. The photons that had been trapped by constant scattering were suddenly liberated to travel freely across the cosmos. The moment of last scattering, when photons stopped interacting regularly with matter, created what we now observe as the cosmic microwave background radiation. This radiation, which fills all of space and can be detected by sensitive instruments today, is the afterglow of recombination. It represents a snapshot of the universe at the moment it became transparent, providing us with direct observational evidence of conditions 380,000 years after the Big Bang. The cosmic microwave background has been cooling ever since recombination due to the expansion of the universe. The photons that were emitted with energies corresponding to 3,000-degree blackbody radiation have been redshifted to much lower energies, corresponding to a temperature of just 2.7 degrees above absolute zero. This radiation pervades all of space and represents the oldest light in the universe that we can directly observe. The pattern of tiny temperature fluctuations in the cosmic microwave background reveals the acoustic oscillations that occurred in the coupled radiation matter fluid before recombination. Regions that were compressed when recombination occurred appear slightly warmer, while regions that were rarefied appear slightly cooler. These temperature variations, typically less than 1 part in 100,000, map out the density fluctuations that would eventually grow into galaxies and larger cosmic structures. The formation of atoms during recombination fundamentally altered the dynamics of cosmic evolution. Prior to this transition, radiation pressure had prevented gravitational collapse of matter on most scales, because photons and electrons were tightly coupled. But once electrons were bound into atoms, this coupling was broken, and gravity could begin to pull matter together without interference from radiation pressure. The decoupling of matter and radiation marked the end of the radiation-dominated era and the beginning of the matter-dominated era. From this point forward, the energy density of matter would exceed that of radiation, allowing gravitational instabilities to grow and eventually form the first cosmic structures. The universe had crossed a threshold from which there was no return, entering a new phase of evolution dominated by the gravitational assembly of dark and ordinary matter. Dark matter played a crucial role during and after recombination, even though it did not participate directly in the atomic formation process. Dark matter particles do not interact electromagnetically, so they were unaffected by the photon scattering that had suppressed structure formation during the plasma era. Dark matter fluctuations had been growing slowly throughout the radiation-dominated period and were ready to accelerate their growth once radiation pressure was no longer a factor. The newly formed atoms found themselves in a universe very different from the one their constituent particles had inhabited just moments before in cosmic time. Space was now transparent, allowing heat and light to radiate away freely. The universe was also much cooler and less dense than during the plasma era, creating conditions that would remain stable for millions of years to come. Hydrogen atoms dominated the cosmic inventory, making up about 3/4 of all atomic matter by mass. Helium atoms comprise most of the remainder, with trace amounts of deuterium and lithium completing the elemental composition. This was an incredibly simple chemistry compared to the rich diversity of elements we see in the universe today. No carbon, no oxygen, no silicon, no iron, none of the heavy elements that make rocky planets and biological molecules possible. The first atoms were also remarkably pure and pristine. They had formed directly from nuclei and electrons that had existed since the first few minutes after the Big Bang, with no complex history of stellar processing or chemical evolution. These atoms carried within them the primordial composition established during Big Bang nucleosynthesis, preserving a record of the cosmic conditions that existed when the universe was just 20 minutes old. The spatial distribution of these first atoms was not perfectly uniform, but contained the subtle density variations that had been imprinted during cosmic inflation and modified by acoustic oscillations during the plasma era. Regions of slightly higher density contained more atoms per unit volume, while underdense regions had correspondingly fewer atoms. These variations would prove crucial for determining where the first stars and galaxies would eventually form. The process of recombination also established the ionization state that would characterize most of the universe for hundreds of millions of years to come. Over 99% of hydrogen atoms were in their neutral ground state, with only a tiny fraction remaining ionized. This high degree of neutrality would persist until the first stars began to shine and reionize the cosmic gas through their ultraviolet radiation. Recombination had different timescales for different regions of the universe, depending on their density and temperature. Slightly denser regions, which were also slightly warmer due to gravitational compression, underwent recombination somewhat later than average. Underdense regions, being cooler, formed atoms earlier. These variations in recombination timing contributed additional structure to the cosmic microwave background and influenced the subsequent evolution of cosmic structure. The electromagnetic spectrum of the universe was dramatically altered by recombination. During the plasma era, thermal radiation had extended across all wavelengths in a perfect blackbody spectrum. But as atoms formed and the universe became transparent, this spectrum was modified by the absorption and emission properties of hydrogen and helium. Photons at specific wavelengths corresponding to atomic transitions were absorbed and re-emitted, creating features in the cosmic spectrum that persist to this day. One of the most important consequences of recombination was the establishment of conditions suitable for gravitational structure formation. With radiation pressure no longer preventing collapse, matter could begin to fall into the gravitational potential wells created by dark matter. The first phase of this process was the formation of dark matter halos, which would eventually become the sites where the first stars and galaxies assembled. The universe after recombination was entering what cosmologists call the Dark Ages, a period when no stars existed to provide light, and the only illumination came from the gradually cooling cosmic microwave background. This might seem like a step backward, a return to darkness after the brilliant plasma era. But this darkness was pregnant with possibility. providing the calm conditions necessary for gravity to begin its patient work of building cosmic structure. The atoms that formed during recombination were not the end of the story, but rather the beginning of a new chapter in cosmic evolution. These simple hydrogen and helium atoms would eventually be gathered by gravity into vast clouds of gas that would collapse to form the first generation of stars. Within the nuclear furnaces of those stars, the heavy elements essential for planets and life would be forged from the primordial material created during recombination. The transition from plasma to atoms represents one of the most profound phase changes in the history of the universe. It transformed space from opaque to transparent, decoupled matter from radiation, and established the conditions necessary for all subsequent cosmic evolution. Every atom in your body can trace its hydrogen content back to this moment when electrons first settled into stable orbits around nuclei in the cooling cosmos. The cosmic microwave background radiation that we observe today is direct evidence of this ancient transition, carrying information across 13.4 billion years of space and time. When radio telescopes detect this radiation, they are literally observing the afterglow of the moment when atoms first formed and the universe became transparent. It is a cosmic fossil that preserves the memory of one of the most important events in cosmic history. Recombination marked the end of the universe's infancy and the beginning of its adolescence, a time when the basic structures that would define cosmic architecture began to take shape. The first atoms were simple and pure, but they carried within them the potential for all the complexity that would follow. From these humble beginnings would emerge stars, planets, chemistry, biology, and ultimately conscious observers capable of understanding their own cosmic origins. After the dramatic transition of recombination, the universe entered a period that cosmologists have aptly named the Dark Ages. This era, lasting from roughly 400,000 years to several hundred million years after the Big Bang, was characterized by an absence of starlight that would seem profound by modern standards. Yet beneath this cosmic darkness, some of the most important processes in the history of structure formation were quietly unfolding. The universe during the Dark Ages was not completely devoid of light, but the only illumination came from the gradually cooling cosmic microwave background radiation. This afterglow of recombination was steadily redshifting to longer wavelengths and lower temperatures as space continued to expand. What had once been visible light when atoms first formed was becoming infrared radiation and eventually radio waves as the universe aged and cooled. The temperature of the cosmic microwave background radiation dropped steadily during this period, falling from the 3,000 degrees present at recombination to perhaps a few hundred degrees by the end of the Dark Ages. This cooling followed a predictable pattern, with temperature decreasing in inverse proportion to the scale factor of the expanding universe. The universe was becoming not just darker, but colder, creating conditions that would remain stable for hundreds of millions of years. In this cooling cosmos, the newly formed atoms of hydrogen and helium drifted through space in vast, tenuous clouds. The density of this primordial gas was extraordinarily low by earthly standards, containing only a few atoms per cubic centimeter. Yet this represented the densest concentration of ordinary matter that existed anywhere in the universe at the time, since no stars or planets had yet formed to create regions of higher density. The gas clouds were not perfectly uniform, but contained the subtle density variations that had been imprinted during cosmic inflation and modified by acoustic oscillations in the pre-recombination plasma. These fluctuations were tiny, typically amounting to variations of only 1 part in 100,000 in the density of matter. But in the patient arithmetic of cosmic time, even such small differences would eventually grow into the largest structures in the universe. Dark matter played the leading role in this early phase of structure formation. Unlike ordinary matter, dark matter had not been affected by radiation pressure during the plasma era because it does not interact electromagnetically. Dark matter particles had been slowly clumping together under their own gravity throughout cosmic history, building up overdense regions that would serve as the scaffolding for all future structure formation. These dark matter halos were invisible, betraying their presence only through their gravitational effects on the surrounding ordinary matter. As dark matter condensed into increasingly dense clumps, its gravity began to pull in the nearby hydrogen and helium gas. This was a slow process, since the gas had to lose its thermal energy in order to fall deeper into the gravitational potential wells created by dark matter. The cooling of the primordial gas was a crucial bottleneck for early structure formation. Hot gas has high pressure that resists gravitational compression, but as gas cools, its pressure drops, and gravity can more easily pull it together. During the Dark Ages, the primary cooling mechanism was the expansion of the universe itself, which reduced both the temperature and density of the gas in a predictable manner. However, this cosmological cooling was not the most efficient process for condensing gas into the dense concentrations needed to form the first stars. More effective cooling required the gas to radiate away its thermal energy, but this presented a significant challenge. Hydrogen and helium atoms in their ground states are very poor radiators of energy. They have no easy way to convert their thermal motion into photons that can escape and carry energy away. The lack of heavy elements severely limited the cooling options available to primordial gas clouds. In the modern universe, gas clouds can cool efficiently through collisions with dust grains and through emission lines from heavy elements like carbon and oxygen. But the first gas clouds contained no dust and virtually no heavy elements, forcing them to rely on much less efficient cooling mechanisms. Despite these limitations, some cooling could occur through the excitation of hydrogen atoms to higher energy levels, followed by radiative decay. When hydrogen atoms collided with sufficient energy, they could be excited from their ground state to the first excited level, and then emit a photon as they decayed back down. This process, involving the famous 21 centimeter hydrogen line, provided a weak but persistent cooling mechanism. Another cooling pathway involved the formation of molecular hydrogen, the first molecule in cosmic history. When two hydrogen atoms combined to form a hydrogen molecule, they could vibrate and rotate in ways that single atoms could not. These molecular motions provided additional channels for converting thermal energy into radiation that could escape from the gas cloud, facilitating further cooling and compression. The formation of molecular hydrogen was itself a complex process that required specific conditions to proceed efficiently. Free electrons, left over from incomplete recombination, played a catalytic role in bringing hydrogen atoms together. Cosmic ray interactions and other high-energy processes could also facilitate molecule formation, though these were relatively rare during the Dark Ages. As dark matter halos grew in mass and their gravitational fields became stronger, they began to accumulate more and more primordial gas. The largest dark matter structures that formed during the Dark Ages had masses comparable to those of modern dwarf galaxies, though they contained no stars and emitted no light. These were the seeds from which the first galaxies would eventually grow. The process of gas accumulation in dark matter halos was not smooth or uniform. As gas fell into the gravitational potential well of a halo, it would be compressed and heated by the gravitational energy release. This heating would temporarily halt further infall until the gas could cool and continue its descent toward the center of the halo. The competition between gravitational heating and radiative cooling determined how efficiently gas could condense within dark matter structures. The first regions to achieve significant gas condensation were those with the highest dark matter densities, typically located at the intersections of the cosmic web that was beginning to emerge from the primordial density fluctuations. These locations, where multiple filaments of dark matter converged, provided the deepest gravitational potential wells and the most efficient sites for gas accumulation. The cosmic web itself was a manifestation of the gravitational amplification of the tiny density fluctuations that had existed since cosmic inflation. Regions that were initially slightly overdense attracted more matter and became even denser, while underdense regions lost matter and became increasingly empty. This process created a network of dense filaments separated by vast, nearly empty voids. The mathematical description of this structure formation process involves the complex interplay between gravity, gas dynamics, and thermodynamics. Computer simulations of cosmic evolution during the Dark Ages reveal a universe that was far from static, with dark matter halos growing, merging, and evolving in a complex dance orchestrated by gravitational forces. The largest scales of structure formation during the Dark Ages were limited by the finite age of the universe and the speed of light. Gravity could not yet have organized matter on scales larger than the distance light could travel since the Big Bang, setting a fundamental limit on the size of the first cosmic structures. This horizon scale grew with time, allowing ever larger structures to form as the universe aged. Temperature played a crucial role in determining which dark matter halos could successfully accumulate gas during the Dark Ages. Smaller halos had weaker gravitational fields that could not overcome the thermal pressure of the primordial gas. Only halos above a certain minimum mass, roughly 1,000,000 times the mass of our Sun, could begin to accumulate significant amounts of gas from their surroundings. This mass threshold had profound implications for when and where the first stars would eventually form. The requirement for sufficiently massive dark matter halos meant that star formation would begin in the most overdense regions of the universe, where large halos formed earliest. The first stars would not appear randomly throughout space, but would be concentrated in specific locations determined by the underlying dark matter distribution. The chemical composition of the gas during the Dark Ages remained virtually unchanged from the primordial abundances established during Big Bang nuclear synthesis. Roughly 75% hydrogen and 25% helium by mass, with trace amounts of deuterium and lithium, composed the entire inventory of elements available for the first structures. This chemical simplicity would have profound effects on the properties of the first generation of stars. The absence of heavy elements meant that the first gas clouds could not fragment into small pieces as efficiently as modern star-forming regions. Heavy elements act as coolants, allowing gas to radiate away energy and compress to higher densities. Without this cooling, the first gas clouds remained relatively hot and were likely to form much more massive stars than those typically seen in the modern universe. The Dark Ages were also characterized by the absence of any significant sources of ionizing radiation. Unlike the modern universe, where hot stars and active galactic nuclei flood space with ultraviolet photons capable of ionizing hydrogen, the Dark Age universe contained only the gradually cooling cosmic microwave background radiation. This meant that essentially all hydrogen remained in its neutral atomic state throughout this period. The neutral state of hydrogen during the Dark Ages has left an observational signature that astronomers hope to detect with sensitive radio telescopes. The 21 centimeter emission line from neutral hydrogen should show absorption features against the cosmic microwave background, creating a fossil record of conditions during this early epoch. Detecting this signal represents one of the holy grails of observational cosmology. As the Dark Ages progressed and dark matter halos continued to grow, the universe was gradually preparing for one of the most dramatic transitions in cosmic history. The largest and most massive halos were accumulating enough gas to reach the critical densities and temperatures needed for nuclear fusion. The countdown to the formation of the first stars had begun, though it would still take hundreds of millions of years for these nuclear fires to ignite. The end of the Dark Ages would be marked not by a gradual brightening, but by the sudden appearance of the first stellar light sources. These first stars would be unlike any that exist in the universe today, massive behemoths burning through their nuclear fuel at prodigious rates. When they finally formed, they would transform the universe from a dark, cold place into one filled with light, heat, and the first heavy elements beyond hydrogen and helium. The gravitational structures that formed during the Dark Ages provided the foundation upon which all subsequent cosmic evolution would build. The dark matter halos that emerged from this period became the sites where galaxies would eventually form. The gas that accumulated in these halos would become the raw material for the first stars. The cosmic web that began to take shape during this era continues to define the largest scale structure of the universe today. Looking back on the Dark Ages from our modern perspective, we can appreciate this period as a time of patient preparation, when the universe was setting the stage for the spectacular light show that would follow. The darkness was not empty, but pregnant with possibility, as gravity slowly but inexorably gathered the raw materials needed for the next phase of cosmic evolution. The atoms that had formed during recombination were beginning their long journey toward becoming parts of stars, planets, and eventually living organisms. Though they drifted in darkness for hundreds of millions of years, they were moving toward a destiny that would see them forged in stellar furnaces, dispersed by supernova explosions, and ultimately assembled into the complex chemistry that makes life possible. The Dark Ages represent the calm before the storm, a period of steady gravitational assembly that would soon give way to the violent nuclear fires of the first stars. When those stars finally ignited, they would not only end the cosmic Dark Ages, but begin the process of chemical evolution that would transform the universe from a simple mixture of hydrogen and helium into the rich periodic table of elements we see today. After hundreds of millions of years of cosmic darkness, the universe was about to witness the birth of its first sources of light since the plasma era ended. Deep within the most massive dark matter halos, primordial gas clouds had been slowly accumulating and cooling, reaching the critical densities and temperatures needed to ignite nuclear fusion. The formation of the first stars marked not just the end of the Dark Ages, but the beginning of a new phase of cosmic evolution that would transform the chemical composition of the universe forever. These first stars, known to astronomers as population 3 stars, were unlike anything that exists in the universe today. Born from gas clouds containing only hydrogen and helium, they lacked the heavy elements that help modern stars regulate their formation and evolution. Without carbon, oxygen, and other metals to facilitate efficient cooling, the primordial gas clouds could not fragment into small pieces as they collapsed under gravity. Instead, they formed individual stars of enormous mass, typically 50 to 100 times more massive than our Sun. The nuclear fires that ignited in the cores of these stellar giants burned with an intensity that dwarfed even the most luminous stars in the modern universe. Their surface temperatures reached 50,000 degrees or more compared to the 6,000 degrees of our Sun's surface. They blazed with the light of millions of ordinary stars, their nuclear furnaces consuming hydrogen at prodigious rates that would exhaust their fuel in just a few million years. But the true significance of these first stars lay not in their brightness, but in their role as cosmic alchemists. For the first time since Big Bang nucleosynthesis, nuclear reactions were creating new elements heavier than lithium. In the extreme temperatures and pressures of stellar cores, hydrogen fused into helium, helium fused into carbon, and carbon fused into even heavier elements. The first stars were literally cooking up the periodic table, forging the chemical diversity that would make planets and life possible. The nuclear fusion process in stellar cores follows a well-understood sequence of reactions that build progressively heavier elements. Hydrogen fusion, which powers most of a star's lifetime, combines 4 hydrogen nuclei to form one helium nucleus. releasing energy according to Einstein's equation E equals mc squared. When the hydrogen in the core is exhausted, helium fusion begins, producing carbon and oxygen through the famous triple alpha process. As the star evolves and its core temperature rises, successive fusion reactions create neon, magnesium, silicon, and ultimately iron. Each fusion stage burns faster than the previous one, creating an accelerating sequence of nuclear evolution. A star might burn hydrogen for millions of years, helium for thousands of years, and the final silicon burning phase for just a few days before reaching the iron core that signals the end of nuclear energy generation. Iron represents a fundamental barrier in stellar nucleosynthesis because it has the highest binding energy per nucleon of any nucleus. Fusing iron into heavier elements requires energy input rather than releasing energy, so once a massive star builds up an iron core, nuclear fusion can no longer provide the pressure needed to support the star against gravitational collapse. The stellar core, containing about 1.5 times the mass of our Sun, compressed into a sphere just 20 kilometers across, becomes gravitationally unstable. The collapse of the iron core triggers one of the most violent events in the universe, a core collapse supernova. In less than a second, the core implodes to nuclear density, forming a neutron star or black hole, while releasing more energy than our Sun will produce in its entire 10 billion year lifetime. The shockwave from this collapse races outward through the star, heating and disrupting the overlying layers and ejecting them into space at speeds of thousands of kilometers per second. The supernova explosion serves as a cosmic recycling center, dispersing the heavy elements forged in the stellar core throughout the surrounding interstellar medium. Elements from carbon to iron, created during the star's lifetime, are blasted into space, along with even heavier elements synthesized during the explosion itself. The intense neutron flux during the supernova creates elements beyond iron through rapid neutron capture, producing gold, platinum, uranium, and other heavy elements that cannot be made in normal stellar burning. The first supernovae were transformative events that fundamentally altered the chemical composition of the universe. Gas clouds that had contained only hydrogen and helium suddenly found themselves enriched with carbon, oxygen, silicon, iron, and dozens of other elements. This chemical enrichment, though initially tiny compared to the abundance of hydrogen and helium, provided the seeds for more complex chemistry and more efficient star formation in subsequent generations. The heavy elements dispersed by the first supernovae acted as coolants that dramatically improved the efficiency of gas cloud collapse. Carbon and oxygen atoms could emit photons at infrared wavelengths, providing new channels for gas clouds to radiate away their thermal energy. This enhanced cooling allowed gas clouds to fragment into smaller pieces during collapse, leading to the formation of less massive stars that could burn for billions of years rather than just millions. The transition from population 3 stars to population 2 stars, which contained small amounts of heavy elements, marked a fundamental change in the character of stellar evolution. While the first stars were short-lived giants that lived fast and died young, subsequent generations included a full spectrum of stellar masses. Low-mass stars, similar to our Sun, could form for the first time, providing stable sources of energy that would burn for billions of years. These longer-lived stars created new opportunities for planetary system formation and potentially for the development of life. The heavy elements they dispersed through stellar winds and eventual supernova explosions continue to enrich the interstellar medium, gradually building up the chemical complexity that characterizes the modern universe. Each generation of stars built upon the chemical legacy of its predecessors, adding new elements and increasing the abundance of existing ones. The process of stellar nucleosynthesis follows well-established nuclear physics principles that allow astronomers to predict which elements should be produced in different types of stars. Massive stars, which reach higher core temperatures, can fuse elements all the way up to iron. Lower mass stars stop at earlier stages, producing primarily helium, carbon, and oxygen. The most massive stars, those exceeding about 25 solar masses, may collapse directly to black holes without producing supernovae, potentially trapping their heavy elements forever. Intermediate mass stars, roughly 3 to 8 times the mass of our Sun, follow a different evolutionary path that creates its own distinctive pattern of element production. These stars develop dense, hot cores, but are not massive enough to trigger core collapse supernovae. Instead, they lose their outer layers gradually through stellar winds, creating beautiful planetary nebulae while exposing their carbon-rich cores as white dwarf stars. The white dwarf remnants of intermediate mass stars can participate in their own type of supernova if they accrete material from a companion star. Type Ia supernovae occur when a white dwarf accumulates enough material to exceed the Chandrasekhar limit, triggering a thermonuclear explosion that completely destroys the star. These explosions are particularly important for producing iron peak elements and for dispersing them throughout galaxies. The chemical evolution of the universe proceeded through billions of years of stellar birth, evolution, and death. Each cycle of star formation incorporated the heavy elements produced by previous generations, gradually building up the metallicity of the interstellar medium. This process was not uniform throughout space, but proceeded faster in regions with higher star formation rates, creating chemical gradients within and between galaxies. The Sun itself is a third-generation star, formed from gas that had already been enriched by countless previous generations of stellar evolution. The heavy elements in our solar system, from the iron in our blood to the calcium in our bones, were forged in the nuclear furnaces of ancient stars and dispersed by supernova explosions that occurred billions of years before the Earth formed. The story of stellar nucleosynthesis reveals the intimate connection between cosmic evolution and the chemistry of life. The carbon that forms the backbone of organic molecules, the oxygen that we breathe, the phosphorus in our DNA, all were created in stellar cores and distributed through space by stellar explosions. We are quite literally made of star stuff, our atoms carrying within them the history of nuclear fusion reactions that occurred in stellar furnaces throughout cosmic time. Stars also played a crucial role in ionizing the universe, ending the Dark Ages permanently. The intense ultraviolet radiation from the first massive stars began to ionize the neutral hydrogen that filled intergalactic space, creating bubbles of ionized gas around each stellar source. As more stars formed and these ionized bubbles expanded and merged, the universe gradually transitioned from neutral to ionized, a process that was largely complete within the first billion years after the Big Bang. The reionization of the universe had profound effects on subsequent star formation and galaxy evolution. Ionizing radiation heated the intergalactic medium, making it more difficult for small dark matter halos to retain their gas and form stars. This feedback process helped regulate the rate of star formation and may explain why many small galaxies appear to have stopped forming stars early in cosmic history. The legacy of the first stars extends far beyond their role in chemical enrichment. They established the feedback processes that continue to regulate star formation today, created the first black holes that would eventually grow into the supermassive black holes at galaxy centers, and set the stage for the formation of the first galaxies. Their gravitational effects helped shape the cosmic web of dark matter, while their energetic output influenced the thermal and ionization state of the intergalactic medium. Modern observations are beginning to reveal the signatures of population 3 stars in the most distant galaxies observable with current telescopes. These ancient stellar populations, though too faint to be detected individually, leave characteristic spectral signatures in the integrated light of their host galaxies. future space telescopes may be able to observe population 3 stars directly, providing crucial tests of our understanding of early stellar evolution. The transition from the first stars to modern stellar populations represents one of the most important phases in cosmic evolution. It transformed the universe from a chemically simple place containing only hydrogen and helium into a complex system capable of forming rocky planets and supporting the chemistry of life. Every star that shines today is part of this ongoing process of chemical evolution, continuing to forge new elements and disperse them through space for future generations of stars and planets. The nuclear recycling performed by stars over billions of years has created a universe rich in chemical diversity. From the simplest hydrogen atoms, formed during recombination, to the complex heavy elements synthesized in stellar cores, the journey of atoms through cosmic time reflects the creative power of nuclear fusion. Stars have served as the universe's primary mechanism for organizing simple building blocks into the complex chemical architecture that makes planets, life, and ultimately consciousness possible. The heavy elements forged in stellar cores and dispersed by supernova explosions did not simply float through space as isolated atoms. Over billions of years, these recycled stellar materials began to aggregate into increasingly complex structures, eventually giving rise to rocky planets, organic chemistry, and ultimately, life itself. The journey from the first hydrogen atoms to conscious beings capable of contemplating their own cosmic origins represents one of the most remarkable transformations in the history of the universe. As successive generations of stars lived and died, the interstellar medium became progressively enriched with heavy elements. What had once been a universe containing only hydrogen and helium gradually developed a rich chemical diversity that included carbon, oxygen, silicon, iron, and dozens of other elements essential for complex chemistry. This process of cosmic chemical evolution proceeded at different rates in different regions, with areas of active star formation becoming more rapidly enriched than quiescent regions. The accumulation of heavy elements reached a critical threshold roughly 8 to 10 billion years after the Big Bang, when the metallicity of typical star-forming regions became sufficient to support the formation of terrestrial planets. Silicon and iron, produced in abundance by massive stars, provided the raw materials for rocky planet cores and crusts. Carbon and oxygen enabled the formation of complex molecules that could exist in solid, liquid, and gaseous phases under the temperature and pressure conditions found on planetary surfaces. The formation of planetary systems required not just the presence of heavy elements, but also the gravitational influence of stars to organize these materials into coherent structures. As new stars formed from chemically enriched gas clouds, they were typically surrounded by disks of leftover material containing dust grains made of heavy elements. These protoplanetary disks served as the nurseries where planets would eventually coalesce from countless collisions between dust particles, asteroids, and larger bodies. Rocky planets like Earth formed through a complex process of accretion that took millions of years to complete. Initially, microscopic dust grains stuck together through electromagnetic forces to form larger particles. These particles continued to collide and merge, growing into asteroids and eventually planet-sized bodies called planetesimals. The final stages of planetary formation involved dramatic collisions between these large objects, generating enough heat to melt entire worlds and differentiate them into distinct layers. The early Earth that emerged from this violent accretion process was a hellish world of molten rock and toxic atmospheres, bearing little resemblance to the life-supporting planet we know today. The atmosphere contained virtually no oxygen, but was rich in hydrogen, methane, ammonia, and other reducing compounds. The surface was frequently resurfaced by volcanic activity and asteroid impacts, creating an environment that seemed utterly hostile to any form of complex chemistry. Yet within this apparently sterile environment, The chemical diversity inherited from stellar nucleosynthesis began to manifest in increasingly sophisticated ways. Carbon, with its unique ability to form 4 chemical bonds, became the backbone of organic chemistry. Combined with hydrogen, oxygen, nitrogen, phosphorus, and sulfur, carbon could form an almost limitless variety of molecules with different properties and functions. The emergence of life from this chemical complexity remains one of the greatest unsolved mysteries in science, but the basic ingredients were clearly present on the early Earth. Amino acids, the building blocks of proteins, could form spontaneously under the conditions that existed in the primordial oceans and atmosphere. Nucleotides, the components of DNA and RNA, also appeared through natural chemical processes involving phosphorus-bearing minerals and organic compounds. The transition from simple organic chemistry to self-replicating life required the development of molecular systems capable of storing and transmitting information across generations. DNA and RNA, constructed from just 4 different nucleotide building blocks, provided elegant solutions to this problem. These molecules could encode vast amounts of information in their sequences while also catalyzing the chemical reactions needed for their own replication. Once self-replication emerged, the process of biological evolution could begin in earnest. Random mutations in genetic sequences, combined with natural selection for traits that enhanced survival and reproduction, led to the gradual emergence of increasingly complex and sophisticated life forms. Single-celled organisms gave rise to multicellular life. Simple body plans evolved into complex organ systems, and basic sensory capabilities developed into sophisticated nervous systems. The evolution of photosynthesis represented a crucial breakthrough that fundamentally altered the chemistry of Earth's atmosphere and oceans. Cyanobacteria learned to harness the energy of sunlight to convert carbon dioxide and water into organic compounds, releasing oxygen as a waste product. This oxygen initially poisoned many existing life forms that had evolved in the reducing environment of the early Earth, but it also enabled the development of more efficient forms of metabolism. The accumulation of oxygen in Earth's atmosphere created new possibilities for complex chemistry and energy production. Aerobic respiration, which uses oxygen to extract energy from organic molecules, is far more efficient than the anaerobic processes that preceded it. This enhanced energy production supported the evolution of larger, more complex organisms with higher metabolic demands. The chemical elements that make life possible all trace their origins back to stellar nucleosynthesis. The carbon in every organic molecule was forged in the core of a dying star through the triple alpha process. The oxygen that powers cellular respiration was created when helium nuclei fused with carbon in stellar interiors. The iron in hemoglobin that carries oxygen through our bloodstream was synthesized during the final moments of a massive star's life, just before it exploded as a supernova. Even the lighter elements essential for life have stellar connections. While hydrogen dates back to the first few minutes after the Big Bang, the specific hydrogen atoms in our bodies have been processed through countless stellar and planetary cycles. Water molecules in our cells may contain hydrogen atoms that were once part of stellar atmospheres, dispersed by stellar winds, incorporated into new star-forming regions, and eventually assembled into the complex chemistry of living systems. The phosphorus in our DNA backbone exemplifies the cosmic connections of biological chemistry. Phosphorus is a relatively rare element that can only be produced in significant quantities during supernova explosions through complex nuclear processes. Every phosphate group in every DNA molecule represents material that was once processed in the nuclear furnace of a massive star and violently dispersed through space by a stellar explosion. The development of complex life required not just the right chemical elements, but also stable environmental conditions maintained over billions of years. Earth's magnetic field, generated by circulation in its molten iron core, protects the atmosphere from being stripped away by solar wind. The presence of a large moon helps stabilize Earth's rotational axis, preventing extreme climate variations that could make complex life difficult to sustain. The chemical evolution that led to life involved countless molecular experiments conducted in primordial oceans, hydrothermal vents, and atmospheric chemical reactions. Most of these experiments led nowhere, producing molecules that quickly degraded or failed to replicate. But a tiny fraction resulted in chemical systems capable of self-organization, growth, and reproduction, eventually giving rise to the biochemical pathways that characterize all life on Earth. The diversity of life that eventually emerged from these humble chemical beginnings is staggering in its complexity and creativity. From simple bacteria that derive energy from sulfur compounds to complex multicellular organisms with sophisticated nervous systems, life has explored virtually every possible niche and energy source available on our planet. Each species represents a unique solution to the challenges of survival and reproduction in specific environmental conditions. The evolution of intelligence represents perhaps the most remarkable development in this 4 billion-year story of increasing complexity. The same carbon-based chemistry that began with simple organic molecules eventually gave rise to nervous systems capable of processing information, storing memories, and engaging in abstract reasoning. The atoms that were once scattered through the cosmos as isolated particles had organized themselves into structures capable of contemplating their own cosmic origins. Human consciousness represents a unique form of cosmic self-awareness, where the universe has evolved to the point where it can study and understand itself through scientific investigation. When we decode the genome of a living organism, we are reading information that has been accumulated through billions of years of evolutionary experimentation. When we study the light from distant stars, we are analyzing photons that carry information about the nuclear processes that created the elements in our own bodies. The development of technology has extended humanity's capabilities far beyond what biological evolution alone could achieve. We have learned to manipulate matter at the atomic level, creating new materials and chemical compounds that do not exist in nature. We have harnessed nuclear energy, the same process that powers stars, to generate electricity and propel spacecraft. We have even begun to understand and modify the genetic code itself, taking an active role in the evolutionary process that created us. Our scientific understanding of cosmic evolution reveals the deep connections between stellar nucleosynthesis, planetary formation, and biological evolution. The same physical laws that govern nuclear fusion in stellar cores also determine the chemical properties of the organic molecules that make life possible. The gravitational forces that assembled the first dark matter, halos, eventually led to the formation of galaxies, stars, planets, and the complex gravitational environment that enables stable planetary orbits. The emergence of life and intelligence appears to be a natural consequence of the increasing chemical complexity made possible by stellar nucleosynthesis. Given sufficient time and appropriate environmental conditions, the heavy elements produced by stars seem inevitably to organize themselves into increasingly sophisticated structures. The exact forms that life takes may vary depending on local conditions, but the underlying chemical principles are universal. The story of cosmic evolution from hydrogen to humans illustrates the remarkable creative potential inherent in the laws of physics and chemistry. Starting from an initial state of almost perfect simplicity, the universe has spontaneously generated structures of enormous complexity through the patient operation of natural processes over cosmic timescales. Stars, planets, life, and intelligence all emerge naturally from the fundamental properties of matter and energy. This perspective reveals humanity's place in the cosmic story not as separate from nature, but as a natural product of cosmic evolution. We are not external observers of the universe, but integral participants in its ongoing development. Our consciousness represents the universe becoming aware of itself. Our science represents the universe understanding itself, and our technology represents the universe learning to consciously direct its own evolution. The atoms in our bodies have participated in this cosmic journey from the very beginning, traveling through stellar furnaces, supernova explosions, molecular clouds, and planetary formation before eventually becoming organized into the complex chemistry of life. We are temporary arrangements of cosmic material assembled through 4 billion years of biological evolution from elements forged in the hearts of dying stars billions of years ago. Looking ahead, the story of cosmic evolution continues through us, and the civilizations we may eventually create. The same creative processes that transformed hydrogen into stars, stars into heavy elements, and heavy elements into life, may now operate through conscious intelligence to create forms of complexity and beauty that we can barely imagine. The journey from atoms to awareness is not ending, but entering a new phase where conscious beings become active participants in cosmic evolution itself. As we reach the end of this cosmic journey from energy to atoms to awareness, we can step back and marvel at the extraordinary transformation that has unfolded over 13.8 billion years of cosmic time. What began as a universe filled with pure energy and quantum fields has evolved into a cosmos containing stars, planets, chemistry, biology, and conscious beings capable of understanding their own origins. The story of how atoms formed from nothing is really the story of how complexity emerges from simplicity through the patient operation of physical laws. Yet when we speak of something arising from nothing, we must be careful to understand what nothing really means in this cosmic context. The universe did not emerge from a philosophical void, an absolute absence of everything. Instead, it arose from a quantum vacuum filled with fields and governed by mathematical laws that seem to be woven into the very fabric of reality itself. The nothing from which our universe emerged was pregnant with potential, containing within it all the possibilities that would eventually manifest as matter, energy, space, and time. The quantum fields that permeate all of space represent a deeper level of reality than the particles we observe in everyday experience. Electrons, protons, photons, and all other particles are really excitations or vibrations in these underlying fields. The apparent solidity of matter is an emergent property that arises when these field oscillations interact and organize themselves into stable patterns. What we call atoms are actually persistent whirlpools in the quantum field ocean, temporary arrangements of energy that maintain their identity for billions of years. The mathematical laws that govern quantum field behavior appear to be universal constants, applying everywhere and everywhen throughout the cosmos. These laws are not imposed from outside, but seem to be intrinsic properties of existence itself. They determine how energy can transform into matter, how particles can interact, and how complex structures can emerge from simple components. The fact that such laws exist at all represents one of the deepest mysteries in science and philosophy. Einstein's equation E equals mc squared serves as the fundamental bridge between energy and matter in our cosmic story. This deceptively simple formula encapsulates one of the most profound truths about the nature of reality. Energy and matter are not separate substances, but different manifestations of a single underlying unity. The equation tells us that matter is simply crystallized energy, while energy is liberated matter. Every atom in your body represents energy that has been locked into material form through the operation of this fundamental relationship. The process by which energy condensed into the first particles required conditions so extreme that they can barely be imagined. Temperatures exceeding 100 million trillion degrees created an environment where the distinction between matter and energy became meaningless. Particles and antiparticles appeared and vanished in cosmic fractions of seconds, while the fundamental forces of nature existed in unified states that have no analogue in the modern universe. The survival of matter through the Great Annihilation represents one of the most remarkable accidents in cosmic history. For every billion particles of matter that existed in the early universe, there were billion particles of antimatter. They should have completely destroyed each other, leaving behind only a sea of photons in an empty cosmos. Instead, a tiny asymmetry of 1 part in a billion allowed a minuscule fraction of matter to survive. Every atom that exists today is a descendant of those few survivors, refugees from the most complete destruction ever witnessed in the universe. This cosmic near-miss raises profound questions about the nature of physical laws and the apparent fine-tuning of the universe for complexity. If the matter-antimatter asymmetry had been even slightly different, no atoms could have formed. If the nuclear forces had been marginally stronger or weaker, stellar nucleosynthesis could not have produced the heavy elements essential for chemistry and life. If gravity had been significantly different, stars and galaxies might never have formed at all. The precise values of the fundamental constants seem to be exquisitely calibrated to allow the emergence of complexity. This observation has led some scientists to propose that our universe is just one of countless others in a vast multiverse with different physical laws and constants. In such a scenario, we exist in this particular universe precisely because its laws permit the formation of atoms, stars, planets, and life. Other universes with different constants would remain simple and lifeless, with no observers to contemplate their sterile perfection. Yet regardless of whether our universe is unique or one of many, the fact remains that the laws governing our cosmos have proven remarkably creative. Starting from an initial state of almost perfect simplicity, these laws have generated structures of breathtaking complexity and beauty. The same quantum field fluctuations that were amplified during cosmic inflation eventually became the seeds of galaxies. The nuclear reactions that power stars also forge the chemical elements that make biochemistry possible. The formation of atoms represents a crucial milestone in this cosmic creative process. Atoms are the first stable, persistent structures to emerge from the primordial chaos of the early universe. Unlike the ephemeral particles that existed during the first microseconds after the Big Bang, atoms can survive for billions of years, providing stable platforms for increasingly complex chemistry. Without atoms, there could be no molecules, no chemistry, no planets, and no life. The story of atomic formation also illustrates the importance of cooling and expansion in cosmic evolution. The early universe was too hot and dense for stable structures to exist, but as space expanded and temperatures dropped, new levels of organization became possible. First, quarks could bind into protons and neutrons. Then nuclei could survive without being immediately torn apart. And finally, electrons could settle into stable orbits around nuclei to form neutral atoms. Each of these transitions occurred at specific temperature thresholds, determined by the binding energies of the structures involved. The universe had to cool below 10 trillion degrees for quarks to be permanently confined in protons and neutrons. It had to drop below 1 billion degrees for nuclei to survive long enough to participate in fusion reactions. It had to reach 3,000 degrees before electrons could be captured into atomic orbitals. These temperature markers represent fundamental milestones in the organization of matter. The cosmic microwave background radiation that we observe today provides direct evidence of the moment when atoms first formed and the universe became transparent to light. This ancient radiation, stretched and cooled by 13.4 billion years of cosmic expansion, carries within it the imprint of conditions when the cosmos was just 380,000 years old. When radio telescopes detect this radiation, they are literally observing the afterglow of atomic formation. The chemical simplicity of the first atom stands in stark contrast to the rich diversity of elements we see in the universe today. The primordial cosmos contained only hydrogen and helium, with trace amounts of deuterium and lithium. There was no carbon to form organic molecules, no oxygen to enable complex chemistry, no silicon to build rocky planets, no iron to create magnetic fields. The chemical complexity that characterizes the modern universe had to be built up gradually through billions of years of stellar evolution. Stars emerged as the universe's primary mechanism for chemical enrichment, transforming simple hydrogen and helium into the entire periodic table of elements. Each generation of stars built upon the chemical legacy of its predecessors, gradually increasing the metallicity of the interstellar medium. This process of cosmic chemical evolution was essential for enabling the formation of rocky planets and the complex chemistry that makes life possible. The fact that stellar nucleosynthesis produces exactly the elements needed for biochemistry seems almost too convenient to be coincidental. Carbon is produced in abundance by stars and has unique chemical properties that make it ideal for forming complex organic molecules. Oxygen is also produced in large quantities and provides the basis for water and many other compounds essential for life. The relative abundances of elements produced by stellar nucleosynthesis closely match the requirements for building planets and supporting biological chemistry. Life itself represents the ultimate expression of atomic creativity. The same atoms that were forged in stellar cores billions of years ago have organized themselves into systems capable of growth, reproduction, and evolution. The carbon atoms in our DNA, the oxygen atoms in our cells, the iron atoms in our blood, all were once part of massive stars that lived and died long before our solar system formed. We are literally made of recycled star matter, animated by the nuclear energy released when hydrogen fuses into helium in our sun. The emergence of consciousness represents a remarkable milestone in cosmic evolution, where the universe has developed the ability to understand itself through scientific investigation. When we study the cosmic microwave background, we are observing evidence of our own atomic origins. When we analyze the light from distant stars, we are learning about the nuclear processes that created the elements in our bodies. When we contemplate the Big Bang, we are examining the ultimate source of every atom in our universe. This reflexive quality of cosmic evolution, where the universe studies itself through conscious observers, suggests that complexity and awareness may be natural outcomes of the fundamental laws of physics. Given sufficient time and appropriate conditions, matter seems to organize itself spontaneously into increasingly sophisticated structures. From atoms to molecules to cells to organisms to brains to consciousness, each level of organization emerges naturally from the properties of its components. The story of atoms forming from nothing reveals the universe to be far from a random, purposeless collection of particles. Instead, it appears to be a creative system governed by elegant mathematical laws that naturally generate complexity and beauty. The same equations that describe quantum fields and particle interactions also determine the properties of atoms, molecules, and the chemistry of life. There is a deep unity underlying the apparent diversity of natural phenomena. Looking to the future, the creative processes that transformed energy into atoms and atoms into awareness continue to operate through human consciousness and technology. We have learned to manipulate matter at the atomic level, creating new materials and chemical compounds that do not exist in nature. We have begun to understand and modify the genetic code, taking an active role in biological evolution. We may eventually develop the ability to create new forms of matter and energy that transcend the limitations of biological chemistry. The atoms that emerged from the energy-rich beginning of the universe have proven to be remarkably versatile building blocks. They have formed stars and planets, mountains and oceans, forests and animals, brains and thoughts. The same hydrogen atoms that first appeared during Big Bang nucleosynthesis have participated in countless cycles of cosmic evolution, sometimes locked in stellar cores, sometimes floating freely in interstellar space, sometimes incorporated into living systems. Every breath you take contains atoms that have journeyed through this entire cosmic story. The oxygen molecules entering your lungs were forged in the nuclear furnaces of massive stars and dispersed by supernova explosions billions of years ago. They have been part of rocks and oceans, plants and animals, before becoming temporarily incorporated into your body. In a few years, they will move on to participate in other chemical and biological processes, continuing their eternal dance through the cosmos. The carbon atoms in your body have similarly epic histories. They were synthesized through the triple alpha process in the cores of dying stars, ejected into space by stellar winds or supernova explosions, incorporated into new star-forming regions, condensed into planets, and eventually organized into the complex chemistry of life. Each carbon atom represents a survivor of stellar death and rebirth, a testament to the creative power of nuclear fusion. The story of cosmic evolution from energy to atoms to awareness is ultimately a story about transformation and creativity. It shows how the universe has the remarkable ability to reinvent itself, creating new levels of complexity and organization through the operation of simple, elegant laws. What began as a nearly featureless quantum field has evolved into a cosmos containing galaxies, stars, planets, and conscious beings capable of appreciating the beauty and mystery of existence itself. This cosmic perspective reveals the deep connections that link every part of the universe to every other part. The atoms in your body, the light from distant stars, the cosmic microwave background radiation, and the dark matter that shapes cosmic structure are all participants in a single, unified story of cosmic evolution. We are not separate observers of the universe, but integral participants in its ongoing development. The formation of atoms from nothing represents just one chapter in this larger story of cosmic creativity. As the universe continues to evolve and expand, new forms of complexity and organization will undoubtedly emerge. The same fundamental principles that transformed quantum fields into atoms may eventually give rise to forms of matter, energy, and consciousness that we cannot yet imagine. Perhaps most remarkably, this entire cosmic story can be reconstructed from the evidence available to us today. The cosmic microwave background carries information about atomic formation. The abundances of light elements preserve records of Big Bang nucleosynthesis. The heavy elements in our bodies bear witness to stellar nucleosynthesis. Every atom is a fossil that contains information about the cosmic processes that created it. In contemplating how atoms formed from nothing, we are really exploring the deepest questions about the nature of existence itself. Why do physical laws exist? Why do they take the particular mathematical forms that they do? Why is the universe comprehensible to conscious minds? These questions may never have complete answers, but the journey of exploration itself represents one of the highest expressions of the cosmic creativity that began with the first quantum field fluctuations 13.8 billion years ago. The universe has come an extraordinary distance from its energy-rich beginning to the complex atom-based reality we inhabit today. Every star that shines, every planet that orbits, every life form that evolves, every thought that occurs represents a continuation of the creative process that began when energy first condensed into matter in the primordial cosmos. We are all children of that ancient transformation, temporary arrangements of atoms that have organized themselves into patterns capable of contemplating their own cosmic heritage. The story of atoms forming from nothing is therefore not really about nothing at all, but about the profound creative potential that seems to be built into the very foundations of reality. It is a story about how complexity emerges from simplicity, how structure arises from apparent chaos, and how consciousness eventually develops the ability to understand the cosmic processes that created it. In the end, we discover that we are not just observers of the universe, but expressions of its deepest creative impulses, temporary manifestations of the eternal dance between energy and matter that began with the Big Bang and continues through us today.